We're going to start talking about energy by learning about what a system is. And so we'll do that using the example of an apple. So if you were to take an apple, this will be our apple, and it were to fall, as it falls, its kinetic energy would increase because gravity is causing it to accelerate. So we can diagram this with a chart that we call an LOL chart, and I showed you guys an example already. Okay, so this is our LOL chart. When the apple starts, if we're just going to look at the energy contained in the apple, okay? And so the apple will be what we call our system. We're only tracking the energy of the things in our system, and so in this case, our system is the apple. So if you look at the apple by itself, with nothing else around it, we would say that it doesn't have any energy because its kinetic energy initially when we drop it is 0. But as we drop it, that kinetic energy is going to increase. Okay, so we'll show over here that suddenly now we have kinetic energy. So that energy had to come from somewhere though. It didn't just appear. Something had to give it to the apple. And in this case, the thing that gave it to the apple was gravity through the process of work. And so here we have a diagram showing how the apple, as it falls, increases its kinetic energy, and it got that energy from work done by gravity. Okay, well, there's another way we can look at the system, okay, and maybe a simpler way that's going to allow us to basically show where the energy was before and after. Okay, we're going to change our system to be the apple and the earth, which means that we can introduce another kind of energy, because at first there is no kinetic energy from the apple, but the apple does have energy relative to its position above the earth. And so if you think about it, the higher you lift up an apple, the faster it's going to be falling when it hits the ground. And so we're going to call this energy potential energy from gravity. And the way we're going to use for that is a capital U with a subscript G. Now in this case, we're going to say, okay, the potential energy in the apple decreased, and we'll say it was transformed into kinetic energy. So if you look at our diagram over here, we now have 3 bars of kinetic energy, and all of that potential energy is now gone because it was entirely transformed into kinetic energy. And so if you look at this diagram, we show that we started with one kind of energy. That energy decreased as it became kinetic energy, and so now we have this kind. All of this kind is gone now because it went all to here. So the apple fell until it hit the ground, essentially. Now this approach here allows us to eliminate having to use work, because our system here includes all the contributing factors. Okay, and so these things we'll call our system, and anything outside of those we call the environment. And the environment can add energy to the system or take energy away, but we don't track the energy of the environment. And so in a system where the environment adds or takes energy, we call that an open system. And this example right here was of a closed system, because all the energy that we started with, we ended with. Okay, this was an open system before because we started with no energy and then ended up with energy. Now we're going to look at a scenario of someone going down a slide. Okay, it says here we have a kid that's about to go down a slide with a height of 8.5 meters. and we want to know how fast the child's going at the bottom. If you look at the slide, it's curving around. It goes in multiple different directions. And so this would be a really difficult question for us to analyze using any of our other approaches. We can't use kinematics here because the direction keeps changing. And so energy gives us another option for analyzing this type of situation. So what we're going to do is we're going to start by doing an LOL diagram like we did before. Okay, and we're also going to define our system. So looking at this slide, we're going to say that this child is decreasing their height. Okay, which means that we know that their gravitational potential energy is going to have to decrease because they started with some amount and it's going to go to 0 when they get to the ground. And so we're going to make the Earth part of our system, and then the object that we're tracking the energy of, the child, we're going to make that part of our system as well. Okay, and as we look, we're going to say, okay, well, the child starts from rest, which means our kinetic energy is going to be equal to 0. And it starts way up high on the slide, which means that we're going to start with some amount of potential energy. Okay, and actually, instead of using that, we're going to use capital U like I showed you before. So we're going to show maybe 3 bars of this. This will be a closed system. There were no friction to take energy out of the system. And so what's going to happen as the child goes down the slide, that gravitational potential energy will decrease and transform into kinetic energy. And so where we had gravitational energy once potential energy once before, now it's all going to be gone. And in its place, it will have turned into kinetic energy. Okay? Now from this point, the reason why we use these bar charts is because they're very useful. Once we have analyzed the situation here, we can now go ahead and write an equation. We'll put the equal sign under the circle. And so we're going to say, okay, kinetic energy is 0. Well, kinetic energy is 1/2 mv squared. Okay, potential energy mgh. Okay, on the other side, 1/2 mv squared for kinetic energy, and then mgh for potential, and we'll call this h1, we'll call this h2, we'll call this v1, and this v2. Okay, so as we said, we have 0 kinetic energy to start, so we're going to take away that because it's equal to 0, just like our gravitational potential energy at the end, which means that we start with gravitational potential energy and end with kinetic energy. Okay, so now we can solve this. Alright, the m is going to drop out from both sides. Okay, we're finding the child's speed, so we're going to solve for v. So we have g times h equals 1/2 v squared. We can multiply the 2 over, so v squared equals 2gh, so that v equals the square root of 2gh. If you punch this in your calculator, you're going to get that the velocity of the child at the bottom of the slide is 12.9 meters per second. Okay, so now the one thing we don't know from this scenario is what direction the child is going. So that's information that we lose when we use energy to analyze something, but it's a trade-off because by losing direction, we gain a tool that allows us to simplify a problem we're working on. The last thing I want to mention is for this child to be going 12.9 meters per second at the bottom of the slide. That would mean they're going almost 30 miles per hour, which I don't know how fast kids go in water parks and slides, but that would be, seems to me, a little bit dangerous. So anyway, if you have any questions, please submit them at the link below the video, and thank you for watching.